Hello, Algebra 2. Here we are of our last lesson of the week, also the last section of Chapter 6. So we'll be finishing this up today. We'll be talking about the graphing of polynomial functions. The introduction to this section is really good also in providing you with some information on how to use your graphing calculators. So that's something I want you to look at on your own and review. We've done some of this kind of stuff before in class, so it should be a review to you. And again, next week when we get back together, we'll be able to go over anything that you're struggling with as well. But please do reach out if you have any troubles along the way here. So without further ado, let's jump into section 8 of chapter 6 together. All right, as a quick way of review, if we're evaluating a polynomial, in this case with the number 2, we're going to plug that in wherever we see an x. And so if we do that, what answer do we get? Pause the video, work it out yourself. All right, if you plug in 2 for each of those, you should get an answer of negative 39. And if you didn't, rework it until you get to the negative 39. On this next one, it asks us to use synthetic division to divide. So we're dividing this polynomial by this binomial. Remember, what we do through synthetic division is we take this guy and just change the sign on it. We put it as a 1, we put it inside the box, and then we write the coefficients of the polynomial one by one. So we would be 1, then -1, -26, +31, and -5. Let me get you started. You'll bring this 1 down, multiply the 1 by 1 and get 1, and then we add down and we get a 0. So 0 times 1 is just 0. Comes a -26. -26 comes up here. We add down, we get a 5. 5 times 1 is 5. Becomes 0. So remember, then we work backwards through this. So that 5 is going to be our constant. Then the next one, the -26, is an x. Almost forgot my plus here for the 5. And then on the 0, that's our x squared, so it just isn't there at all. And then the next one would be our x cubed. So the x cubed minus 26x plus 5. Which is exactly the right answer. All right. Now, if we want to do the same thing with this guy, remember we'll put the synthetic division here and we'll use 5 instead. And see if you can work this one out on your own. Pause the video. Try it out. Well, if you did it correctly, you should have gotten an ultimate answer of this after you divided. Okay, so the maximum number of real zeros for a function is equal to its degree n. We remember that last time together. So let's look at some of the potential graphs when we actually graph these various functions. So if we have a constant like just something equals, p of x equals 2, where the n, remember this is the power that the x is being raised to, is just 0, then we just get a straight line. But if we have n1, which means x to the first power, then that means that we have a linear equation like this. If we have a quadratic, notice that it has this kind of parabola shape. Once we go to a cubic, so x cubed, it looks kind of like this. A quartic, notice what happens here. And then the quintic, look at what happens. So notice that once you get further and further away from the origin, eventually these guys head off towards infinity one direction or the other. Whenever it's an even based power, notice that the ends of them both are looking up, or if we had a negative in front of it, they would both be pointing down. Similarly, here's another even power, and so you see that they're both pointing upward. Or if there was a negative in front of this x to the 4th, it would be both pointing downward. But with the cubic and quintic, notice that one goes down and the other one goes up. And again, as you can imagine, if I was to put a negative in front of this first power, we would just flip it. This one would be up and this one would be down. So just be familiar, first of all, with the end behavior of these functions. If it's an odd value, one will be up, one will be down. If it's an even value, they'll both be up, or they'll both be down on the end. And then notice how many times these cross the x-axis. Notice for the cubic, it crosses it 3 times. Notice for the quadratic, it crosses twice. For the linear, it's once. For the quartic, it crosses 4 times here. For the quintic, it's crossing it 5 times. Now, This might not always be the case because the quadratic might actually be positioned up or down such that it doesn't actually cross here, which means in those cases you have complex roots that are not real roots, but we'll look at those together. All right, so a function's end behavior describes its values on the left as x approaches negative infinity, and on the right as x approaches positive infinity. So whenever we have even degrees, note here that as x approaches negative infinities, we go this direction, the value of the y, the p of x, approaches positive infinity. And as we approach positive infinity with x, the p of x also approaches positive infinity. It's going up either way. Notice on this guy, with the negative in front of the even numbered power, you notice that they're both going down. The idea with what happens here, guys, is that this term in the polynomial, once the x gets big enough, just overpowers what these guys do. When x gets really, really big, all that really matters in the end really becomes this guy. And so that's why the end behavior is always determined by whatever is going on with the leading term of the polynomial. Notice here when we have an odd number of power, here we have a 3, and here we have a 5, notice that we have opposite end behaviors. One goes down, the other one goes up. If this is positive here, then that means that whenever we're in the negative region of x, it's approaching negative infinity, but when we go positive x, it approaches positive infinity. But if we put a negative in front of it, it just flips that. So then it's positive infinity when x is negative, and negative infinity when x becomes positive. So do make sure that you go over those charts in your book. It does go over those quite well on pages 272 and 273. Make sure you're familiar with those. The two end behaviors of an even degree polynomial function are the same. The two end behaviors of an odd degree polynomial function are different. One goes up, one goes down. Polynomial functions of odd degree must have at least one real zero. Notice that this must be the case because if one end goes up and the other one goes down, at some point in time, if they're going to positive and negative infinity, at some point in time, it will cross the x-axis. There will be one real zero. There will at least be one real zero. So given the polynomial x cubed minus 2x squared minus 5x plus 6, state the function's end behavior. Well, we know since this is positive on this leading term, we know that as x gets more and more negative, so as this number gets more and more negative, so just imagine negative 1 million, and then cubing that, it'd be a hugely negative value. And so that's going to approach negative infinity. But if we put in a positive large number, like positive 1 million, and we cube that, that's going to be a very, very large positive value that we get out. So it's going to approach positive infinity as x gets bigger and bigger. It says here then, describe the number of complex and real zeros. Well, because it's an odd function, remember what I said, if one's going up and one's going down, then there has to be a point in which it crosses the x-axis. So there must be at least one real root. It will have a total of 3 roots because of our other principle that this value, the value on the highest, the power of the highest term in the polynomial, sets the number of roots that we have. So we have exactly 3 complex roots, but there must be at least one real root where it actually crosses the x-axis because it's an odd valued, it's an odd number on this leading term. The other two may be imaginary or they may be real. So in graphing p of x, finding the graph's zeros can be helpful. The constant term identifies the y-intercept, and be sure to illustrate the function's end behavior. So in this case, x cubed minus 2x squared minus 5x plus 6. Well, we can determine from this that x minus 1 is a factor of p of x, and if we do that, we can use synthetic division to get this out of it, x squared minus x minus 6, which can be further factored into x minus 3 times x plus 2. So notice that these are now all the zeros. We have 0 at x equals 1, we have a 0 at x equals 3, and we have a 0 at x equals negative 2. So -2, 0, 1, 0, and 3, 0, we have zeros. We also can plug in 0 for x and get out a value of 6. So we know that's the y-intercept, 0, 6. We can also then find some other ordered pairs and then graph this on a graph. So notice we find those zeros, those become helpful as knowing when the graph is crossing those. We know that it's 0, 6 for the y. So we know that it's making some sort of S shape going through here. And again, you can get more precise by plugging in some other values here and then drawing a somewhat smooth curve. That's if we're doing it by hand. So just a little bit of terminology. The relative minimum happens whenever we see a spot where it turns, where the graph turns. So that's a relative minimum. It's at a valley. And then relative maximums happen wherever there's like a peak, like right up here. Also called turning points or extrema. Now, knowing the basic shapes of different polynomial functions can help you choose a model that best describes a given set of data. And what I want you to do is to review example 3 in your book on page 275. It really does do a good job of walking you through the steps required for you to use your TI-84 graphing calculator whenever you're trying to solve for roots. So I do want you to look through that and with your calculator out, work through the steps so you know how to do it. We have done some things like this before, but this is a good review for you to do. Now, example 4 asks us to find the cubic and quartic polynomial functions modeling the birth rate in the United States from 1910 to 1970. And what it does is it says, let's let x represent the number of years after 1900. And then they put this into the calculator using the stat plot function. So what you would do here is 1910 just becomes 10. This becomes 20, 30, 40, and so on. And when you put in all of that information, you can make a scatter plot and then ask the calculator to make a regression. Because I don't have a really good way of recording myself doing this, I will work some of this with you in class if you have trouble doing it when we get back together next week. But if you do this, you should get a scatter plot that looks something like this. If you zoom in the plot to this kind of similar zoom scale for the window. And then notice here you have both the cubic and the quartic functions here. So the cubic is the green, the quartic is the red. And notice that they both do a decent job of approximating the data that's there. Perhaps the quartic is just a little bit better when we're looking at it. But I also want to just make a comment about how regressions work and what they're useful for and what they're not so useful for. See, the quartic has a much higher R² value, but it appears to be a better fit for the data. Its prediction for 1980, though, is not possible. This is because polynomial functions can be useful for interpolating, but are often not very reliable for extrapolating. Remember, interpolating is when we're looking at data in between data points, the set of data points that we have. But extrapolating is when we're looking beyond the data points that we have at present. And so especially if we're doing population modeling, when you're extrapolating, you're guessing at where the population is going to go from here. The problem with that is that there's a whole lot of factors that might flow into that, and so it's not always all that helpful. This might be something similar to this kind of idea as the modeling that happens for us here in Houston whenever a hurricane is coming our way, where they have all these different models of the projection of where the hurricane might go. And again, there's a lot of variation between those models because models might do a good job of explaining the phenomenon that's already happened. That's interpolation. But when you're trying to extrapolate, when you're trying to get data beyond the data points that you actually have, and you're making guesses about that, a lot of times these models are not very good at doing that work. Notice what would happen in these cases with the quartic and the cubic. In both cases, the end of this is pointing downward, which means that they would say that the population eventually goes to 0, or births go to 0, which is not very likely, right? So in this case, we can see that it didn't go to 0. It just kind of steady, went down, kind of a downward slant here. So maybe looking at this data, something of a linear regression might even look a little bit better. over the longer haul here. So just recognize that these can be really good at interpolation, at showing the variation within the data, but when you get outside of the data, it might not be all that helpful. This is always a danger for statistical analysis, and this is the reason why even in politics and otherwise, sometimes this data can be used to manipulate people into thinking one thing or another, and it's not actually true when you start extrapolating. All right, well, I think we've said enough this week. So here for 6.8, I want you to work on problems 2 through 30 and 44 through 52, the evens. This is on pages 276 through 279. And as always, let me know if you need any additional help. If I can help you in any way, I'd love to do that. If you guys want to get on a Zoom call, I'm more than happy to do that as well. Otherwise, I will see you guys next week, and we'll review all of this information, and we'll be looking towards a test in the middle of next week. Thank you guys so much. Hope you guys stay safe and get some rest and relaxation in there as well. God bless you guys.